Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Mr. Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, good people, last week you worked on quadratic patterns. You revised quadratic patterns from grade 11. You worked on arithmetic sequences as well as geometric sequences. So we're just going to extend the knowledge this week. We're going to be looking at arithmetic series and geometric series. Right. See here the lesson objectives for today's lesson. By the end of this lesson, you should be able to explain what is meant by the concept series, derive and apply the formula for an arithmetic series, derive and apply the formula for geometric series. Remember, those derivations, good people, are examinable. It's part and parcel of book work in paper 1. So you should be able to derive those two formulas. The derivations are examinable. Right, solve problems involving the sigma notation. Understand the concept of converging and diverging geometric series leading to sum to infinity. Solve problems involving sum to infinite terms. Obviously, we can make reference to our curriculum documents there. The CAPS document, page 12 and 40, speaks to sequences and series, as well as the exam guideline on page 6, the 2021 version of the guideline, the updated one. Right, let's see the knowledge that you bring into this lesson. Patterns, just like you did in grade 11 and you revised last week. Arithmetic and geometric sequences that you did last week. Algebraic simplification and manipulation of formulae, literal equations, as well as the exponents, which are very useful in geometric series. Right, understanding what series means. Understanding what series means. Now, in order for us to understand what series means, we need to see how a series is formed. So a series is created by adding terms of an arithmetic sequence. So if you have terms 5, 8, 11 to 182, if we want to form a series, and then you can see that now we are adding the terms. So the addition of terms there, the sum of the terms represents what we know as a series, or what we call a series. So the series is formed from summing up terms of a sequence. Now we use the symbol Sn to represent the sum to the first n terms of a series. Now in a series 5, 8, 11 to 182, we can see that the sum of the first term is just a 5. The sum of the first two terms at t1 plus t2, that would be 5 plus 8, which is 13. The sum of the first three terms, that would be t1 plus t2 plus t3, that would be 5, 8, 11, which gives us 24 there. So when you sum n terms of a sequence like that, you get that this is t1 plus t2 plus t3 up until you get to the nth term. So that is what a series is about. Yeah, right. Now, let's talk to specifics now, to say we are zooming into the type of series that we want to study, and in this case, we want to study an arithmetic series. An arithmetic series is formed by adding terms of an arithmetic sequence. For example, if you have 4, 11, 18, 25 until 368, then the series is formed by then adding those terms that form part and parcel of the sequence. Now, we can calculate the sum of the first n terms of an arithmetic series by using the formula Sn is equals to n over 2 into n minus 1 d. It's n over 2 into 2a plus n minus 1 d, where s sub n represents the sum of the first n terms, n is the number of terms, a is the first term, and d is the constant difference. However, if the last term of the series is known or given, then we can use that this should be n over 2. There's an error here with my work here. It should be Sn is equals to n over 2 into a plus l, like that. So that is what we are going to use in case we know or we are given the last term of the sequence, right? Now, let us look at the derivation. Let us look at the derivation, the algebraic proof of this particular, the algebraic proof of this particular formula. That is the one that I said it's your book work and you need to know it. You need to know it. So the algebraic proof below applies to all arithmetic series and is examinable. That is very, very important. It's very, very important. It's part and parcel of book work for people 1. Now, we are required to prove that Sn is equals to n over 2 into n minus 1d there, like that. So a is the first term and d is the common difference. N is the number of terms, and the last term L is denoted by a plus n minus 1d. So this makes it a bit easier for us to be able to prove the formula if we are taking it from the perspective of the last term, as Tn is a plus n minus 1d. So now I am going to put up the terms here. A, to move to the second term, obviously it's a plus d. To move to the third term, it's a plus 2d. And then we go on and on up until we get to the last term. Look at the last term is L. So if we want to get the term before the last term, then we subtract D from L. Remember, if we want to go forward to L, we are going to add D. But because we are going back, we are going to subtract D. So here we get that we'll have D subtracted twice. That would be the equation 1 formulated using A, D, and L. Now, to formulate equation 2, we are going to reverse the order. So whatever that we have here, we are going to be writing it backwards like that. Whatever we have in equation 1, we are going to reverse it and write it backwards. You see, L was the last term here. L is the first term there. L minus D was the term before the last. L minus D is the second term. So you flipped around that particular series. So you flipped it around. You took equation 1 and you flip it around. So as you write those terms, you will get your numerical equation 2. Now what you do is you add equation 1 and equation 2. In doing so, you can see you get a plus L, a plus L, a plus L, a plus L. So throughout you are getting a plus L. And remember, this was Sn plus Sn, which gives you 2Sn. Now, working with that, we can see that 2Sn, how many a plus L's are we having? Remember, you can see that we are adding a plus L, a plus L, a plus L. So we are adding a plus L many times. In this case, we are saying we are adding them n times because we don't know how many terms we have, but we know that we will be adding them as a multiple of the number of terms. So if the number of terms is n, then that would be the multiple of that particular a plus L. So we have that this is a plus L into n. Now simplifying further, we can divide by 2. Dividing by 2, you see, now gives us Sn is L over 2 into a plus L. Now, remembering what we opened with here to say Tn is a plus n minus 1d, we can replace L. We can replace L here with what? With n over 2. We can replace L with what? a plus n minus 1d. So when we see L here, we are going to put a plus n minus 1d, because we know that L is a plus n minus 1d, and that ultimately takes us to the proof of the n terms of an arithmetic series, right? Remember, the proof is examinable, so you should be able to do it. Right, we move on. Right, basically, let me just go back again and just quickly explain the concept here. You are going to be taking the values of the arithmetic sequence where the first term is a and where the constant difference is d, and then we are going to say the nth term in the nth position is going to be a plus n minus 1d, but that would be the last term of the sequence, so we'll call it L is equals to a plus n minus 1d. Now, if you are to add the terms now, the first term is a, the second term would be a plus d, the third term would be a plus 2d. Then moving on, getting to the last term L, if you move back 2 steps, you'll have that this is L minus d, that would be the term before, L minus 2d, that would be the term before the presiding term. So now, if you have that equation as equation 1, if you have that as equation 1, now in formulating equation 2, it's quite simple. You are going to reverse equation 1. So the last term becomes the first term, and then the first term becomes the last term. You just flip the terms there, you reverse the order, and then from there you add equation 1 and equation 2, you simplify, you get to the solution set there. Right. Now, let's move on. Arithmetic series application. Let's look at the application of an arithmetic series. First example, calculate the sum of the first 20 terms of an arithmetic series -1, 3, and 7. Remember, you need A, you need D, you need N, and you are given N is 20, and then you want to calculate Sn. So you want to determine the value of A. You can see A is -1, yeah, that is the first term, and then D is T2 minus T1, which would then be 4, because it would be 3 minus 1 there, which would be 4. That is what you are going to start with, and then from there you use the formula for summing up the n terms of an arithmetic series. Let's see. Now, A is -1, as I indicated, N is 20, it was given, D is 4, as we worked it out there, which means that we can calculate the sum of the first n terms of an arithmetic series using n over 2 into 2a plus n minus 1d. Now we can substitute the given values. We've substituted n as 20, we've substituted a as -1, we've substituted d as 4, and then we can then simplify that in our calculators. We get that the sum to the first 20 terms of this arithmetic series is 740. Right, I hope that still makes sense. We move on. This is an activity now. I want you to try and work out the sum of the series in this activity. I am going to give you just 4 minutes. It's not a difficult or a long problem, so I'm just going to give you 4 minutes to work through that, and your 4 minutes time starts now. Hello and welcome back. Hopefully you were able to work through this problem. Now, if you check this problem, it's just slightly different from the one that I did as an example, just slightly different, because in the one that I did as an example, we were told that you have 20 terms, but here you are given the last term as triple one, so you don't know how many terms you are adding. So because of that, you have to start by calculating the value of n to know how many terms you are adding. Then you can use the results to calculate the sum to the n terms, right? So point of departure, obviously we identify a d and a tn as triple one. Those are the given information here. A is the first term, D is the difference between the terms, and then from there, as we move on with that, we want to work out with our step one to work out the number of terms that we are adding in this particular series, right? So we substitute the given information to the arithmetic formula because we want to know what n is. So substituting that, and then we can then be able to simplify. Obviously we distribute, we apply the distributive property to distribute the 2 there, simplifying that further. We get 2n is 110, and then we get that n is equals to 55. So now we know the number of terms. So we know A, we know D, we know n is equals to 55. So because of that, means that we know the number of terms that would be adding. Now in doing so, we say that Sn is equals to n over 2 into 2a plus n minus 1d. That is the formula for adding n terms of an arithmetic series. Now, in moving on, we are going to substitute. Where we see a in the formula, we put 3. Where we see d in the formula, we put 2. And where we see n in the formula, we put 55, right? Now simplifying that further and putting our result in the calculator gives us the sum to the first 55 terms, summing up to, you get that they sum up to 3,135. Remember, you can also employ a n over 2 into a plus l because you have the last term. So this would be sum to the first 55 terms. N is 55 over 2, a is 3, and l is 111. Now when you put that into your calculating machine, you get that this is 55 divided by 2 into 3 plus 111, and then when you close that, you get that this is 3,135. So the results are the same. So we can use this or that other one. You can use them interchangeably, but remember, you only use this one if the last term here is given like that. Now, hope that it makes sense and that you were able to work it out on your own. Let us now try to move on. Now we are touching on the geometric series. We are done with the arithmetic series. We are now touching base with the geometric series. So we are saying that a geometric series is formed by adding terms of a geometric sequence. Just like an arithmetic series was formed by adding terms of an arithmetic sequence. So when we added terms of an arithmetic sequence, we got an arithmetic series. Now when we add terms of a geometric sequence, we get a geometric series. Now we also have a formula to calculate the n terms of a geometric series. However, that formula is also examinable. There are two formulas there. I'll explain how you can use them effectively. So you need to know how to derive this formula, because the proof thereof of these formulas is very much examinable as part of book work for paper one. Right now, obviously Sn here denotes the number of it denotes the sum to the n terms, n denotes the number of terms, a is the first term, d is the common difference, and then we are saying that it is much easier to use the formula number 2 if you have that r is less than 1. So it assists you, it makes your work a bit easier so that you don't have to operate with a tedious work there. So the work becomes manageable when you actually use the second formula when r is less than 1. Right. Now let's move on with this the derivation now. Let us look at the derivation, slightly different from the derivation that we just went through for an arithmetic series. Now with a geometric series, we are going to do things just a bit differently. Now let us check now how to formulate the first equation here. You have that if the first term of the geometric series is a, then the next term should be a times r, because to move to the next term we multiply the previous term with the constant ratio. So if you multiply throughout there as you move along the terms, you multiply by the constant ratio, you get that now the nth term, just like we did. Remember in arithmetic we called it L. Here we are not going to call the nth term L. So T sub n here, T sub n represents the nth term. So if you go from the nth term, you take the term before. If you take the term before the nth term, you get that now you should divide by r. If you take the term before that preceding term, you should divide by r again. So that gives us the result a to the n, a times n, or rather a times r to the n minus 2, and the last term is a times r to the n minus 1. Now, what do we do here to generate equation 2? In arithmetic, we reversed. Here, to generate 2, you multiply the whole sequence, the whole series, I should say, of equation 1, you multiply it by r, which means that all the terms that are in equation 1 are going to be multiplied by r. So if you multiply a by r, you get AR. If you multiply AR, you see now this one sends you here. If you multiply AR by R, you get AR squared. If you multiply AR squared by R, you get something over here, which is AR cubed. If you multiply AR to the n minus 3, that was here by R, you get AR to the n minus 2. If you multiply AR to the n minus 2 times R, you get AR to the n minus 1. If you multiply AR to the n minus 1 times R, you get that this is AR to the n. Now you can see that all the terms now have shifted R base, R multiple. They've shifted R multiple to the right. So all the terms have shifted R multiple to the right. Because of that, we are going to then say equation 1 minus equation 2. Equation 1 minus equation 2. I'll repeat the derivation. I'll repeat the explanation of the derivation to that. I'll repeat that quickly. You have that the first term is AR squared for equation 1. To generate equation 2, you multiply each of the terms in equation 1 by R, which means that all the terms would be R multiple. Move R multiple units to the left. So now, if you multiply A by R, you get AR. AR by R, you get AR squared. So you can see that there is a shift in those terms. There's a shift in those terms because they are multiplied by R, which means that the last term will also shift there. Now, from there, we are going to subtract equation 2, equation 1 from equation 2 from equation 1, I should say. We subtract 2 from 1. So it's 1 minus 2. So we get that this is Sn minus RSA. You can see that you will be left with this A because it does not have a partner there. It will subtract 0. But the rest of the terms, you can see that AR and AR take each other out. AR and AR squared, they sum to 0. Or when you subtract them, you get 0. AR to the n minus 2 and AR to the n minus 2, they give you 0. AR to the n minus 1 and AR to the n minus 1, there they give you 0. So you are left with this one as well as negative ARN. So you are left with this term and that term when you subtract the two. Now, because of that, we can actually also take out Sn as a subject. S sub n, we can take it out as a common factor, I should say, not the subject, but the common factor, because you have S sub n here and S sub n there. So if you take it out, you get that you are left with 1 minus r. And then from there, we take out a here as a common factor because a is common to both terms. We get that this is 1 minus r to the n that is left, and then you divide both sides by 1 minus r, and in doing so you get that this formula is generated, but with the condition that r cannot be 1, because if r is equals to 1, then this would be undefined. Right. Hope that you understand the work that we just did. Remember, you must know the derivation. It is very much examinable. Right. Geometric series application. The application of the geometric series. Now, let us look at the application of that. You have that you are given the terms of a geometric series and you are told there are 7, which means n is equals to 7. We see that a is equals to 3. We need to work out r, which is 15 divided by 3, which would then be 5. So r is equals to 5 because it is 15 divided by 3, or 75 divided by 15. So we get that r is 5. So we can take it from there. Now, because our r is greater than 1, we are going to use Sn is equals to a into r to the n minus 1 over r minus 1. Right. Now let's see. There we go. R is equals to 5 as I indicated. A is 3 and n is 7, like that. So now we use that formula. We chose this one because r is greater than what? R is greater than 1. Now, let's go on here. We just substitute the given values into the formula. And then when we simplify, we get that S sub 7 is equals to 58,593. That would be the sum of the first 7 terms of this geometric series, which means if you add term 1, term 2, term 3, term 4, up until term 7, you're going to get that this is 5,800 or 58,593 to be precise, right? Now, there's an activity there. There's an activity also with this one. I tried just to spice it up a bit. I did not give you the number of terms, just like I did with the arithmetic. So you are required to first find the number of terms before you can actually calculate the sum of the series. So I am going to give you 4 minutes to work on this. 4 minutes, strictly 4 minutes. Please work on it as quickly as you can. Your 4 minutes time starts now. Right. Hello and welcome back. Obviously, this is the activity that I gave you here. Now, we're going to look at what is given. A is equals to 0, 25, and then R can be calculated from that. 0, 25 divided by 0, 5 divided by 0, 25, you should get 2. R is 2, and then we are given that Tn is equals to 256. Let me write it properly there. 256, that is Tn. So we are looking for n first, and then we are looking for S sub n as well. So we need to find n first. Doing so, let's see, Tn is AR to the n minus 1. A is 0, 25. Sorry, R is 2. And then Tn is 256. Now, when we substitute the given values into the the geometric sequence formula, and then we get that 256 is equals to 0, 25 times 2 to the exponent of n minus 1. So in simplifying that, we divide both sides by 0, 25. In doing so, we're going to get that 2 to the n minus 1 is equals to 1024. But remember, we are looking for n, so we must be able to check whether we can write 1024 as a base of 2. Must check whether we can write 1024 as a base of 2. Right, we have a slight technical glitch. Just give us a minute, we'll be back just now. Hello and welcome back. Sorry for that. We had just a minor technical glitch, but I think our technicians have worked very hard to resolve that. Let us continue with our work. We had that 2 to the exponent of n minus 1 is 1024, and I was saying we need to be able to express 1024 as a base of 2 so that we can equate the exponents. Now, if we express 1024 as the base of 2, we get that it's 2 to the index of 10, so which means that now we can then apply the laws of exponents. If the bases are the same, the exponents are equal. So if we equate those exponents, we get that n is equals to 11. Now we know how many terms we are adding. We are adding 11 terms, so we can ultimately then go to the sum of the n terms of a geometric series. Remember here, r is greater than 1, r is greater than 1, so we use this formula, r to the n minus 1 over r minus 1. Now we can then substitute the given info. I've substituted a and r into the formula as well as n. So I have that s sub 11, which is the sum to the first 11 terms, would be 511,75. That's how you are supposed to actually work it out. Not a complicated problem, just wanted you to understand the fundamentals. Right. We move on to another activity. Let me check with me here. Yes, we move on to another activity here. How many terms of the geometric series will add up to 2,000 or 20,475? So you're adding 5, 10, and so on. And how many terms are going to sum up to 20,475? I am going to give you 3 minutes to work on that quickly. Just take your 3 minutes and make sure that you are quick in working out your solution so that we can come back and check how you are supposed to work around that. Right, your 3 minutes time starts now. Right, hello and welcome back. Hopefully you were able to work around this nice problem here. So here you can see that we are given the sum. So we have that a is equals to 5, r is equals to 10 divided by 5, or 20 divided by 10, that is 2. And then you are given the sum to the n terms S sub n, which is 20,475, and you are looking for n, right? So we will just substitute into the formula. There's the given info. We use the r minus 1 because r is greater than 1. And then we substitute the given info as is in the formula. We simplify, so 2 minus 1 is 1. This whole numerator divided by 1 retains its value. So you have that 20,475 is equals to 5 into 2 expo n minus 1. So we divide by 5 both sides, we get that 4,095 is 2n to the 2 to the n minus 1. And then from there, if we simplify that any further, we transpose the 1 so that we get that this is 40,096. So we try to express it as a base of 2. We find that it is 2 index 12, 2 exponent 12. So if the bases are the same, the exponents are equal. So n would be equals to 12. That's how you were supposed to actually work it out. Very interesting problem. Very nice problem here. Right, let's move on. We move on now to a new concept, the concept of convergence and divergence. The concept of convergence and divergence. So let us check first that the concept should then ultimately take us to the sum to infinity, or sum to infinite terms. Now, let us consider the two sequences. The one that I placed on the left, let us look at it, and the one that I placed on the right. Look at the one I placed on the left. 1 plus half plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32. You can see that the sequence becomes smaller and smaller, or the terms of the sequence become smaller and smaller here. Now, if you add the first term, S1, S sub 1 gives you 1 because you're adding just one term. S sub 2 gives you 1 plus a half, you get 1.5. S sub 3 gives you 1.75. You can see the numbers are starting to grow a bit. S sub 4, now they no longer grow as much. It's 1,875. S sub 5, 1,9375. S sub 6, 1,98. You see now, it now grows minimal. As you increase the number of terms that you are adding, the growth minimizes. The growth now is minimal. Now, we can see that here we say as n increases, S sub n approaches 2. You can see that the increase is becoming less and less, but these values are approaching, they are approaching 2. They are getting closer and closer to the number 2. Now, mathematically, we say as n gets bigger, as n gets to infinity, S sub n approaches 2. We say as n grows bigger and bigger, S sub n approaches 2. This arrow is saying approaches. You read it as approaches. That's what it means in mathematics. You will see it as you move with your curriculum. S sub n approaches 2 as n approaches infinity. Then this leads us into saying the series converges to 2, because as you add the terms, they get closer and closer to the number 2. So we say that the sum converges. The sum converges to 2. That's basically what is happening, right? Because it gets closer and closer to 2. Now let us look at the sequence on my right. We have 1 plus 2 plus 4 plus 8 plus 32 and so on. Now with this one, you can see that the terms are increasing. The terms are increasing. The value of the terms gets higher and higher as you move from one term to the next. Unlike with the one on the left, when the terms were becoming smaller in value. Right, let's see. If you add 1, S sub 1 is 1, S sub 2 is 3, S sub 3 is 7, S sub 5 is 31, S sub 6 is 63. So you can see as you add more terms, the sum becomes bigger and bigger. So we say as n increases, S sub n becomes very large because you can see that there's an increase here. As n tends to infinity, S sub n also tends to infinity. So we say that the series diverges. It is because it is not getting to the same value. It is becoming bigger and bigger. So unlike converging, this series now is diverging. So we call it a divergent series. Now we want to study further the one that is converging, the one on the left. Sum to infinity of a geometric series would converge, or it will approach a specific value. That is what convergence means. It means that it will approach a specific integral value. So if the constant ratio is the number between -1 and 1. So we found out that for it to converge, there should be a condition for the constant ratio, and that condition is that R should be trapped between -1 and 1. R should be values greater than -1, but values that are less than 1. Right. The value approached by the convergent series is called the sum to infinity. So whatever value that you get as the convergence value is referred to as the sum to infinity of that particular series. Now we can calculate the sum to infinity of a convergent geometric series by using the formula Sn, or S sub infinity is A over R minus 1. This has been derived, good people. This was derived from the sum of the n terms of a geometric sequence, but we'll take equation 2 because R is less than 1. Because R is less than 1, we'll take equation 2. Now, let's see, where does the formula come from? The formula comes from the fact that you have the sum to n terms of a geometric series, and then we know that as n gets bigger, as the value of n, r to the n, it's a mistake here, as the value of n gets bigger and bigger, we get that r to the n gets to approach 0. Because what happens is the constant ratio keeps on getting smaller and smaller as n gets bigger and bigger, because the constant ratio, say maybe it's half. So when the exponent here keeps on increasing, the ratio keeps on decreasing and it approaches 0. So we have that this formula then would then become S sub infinity is A over 1 minus R, because the rest of the things there became 0. Right, we move. Applying the sum to infinity to solve problems, I have an example here that I want us to go through together. We are using the concept of convergence and the sum to infinity. Consider this geometric series 16, 8, and 4. Why does the sum to infinity of this series exist? Why do we say the sum to infinity exists? If they ask you such a question, you need to check the constant ratio, because it exists because the constant ratio is conforming to that condition. Remember, the constant ratio should meet this condition. It should be trapped between -1 and 1. So the series would only the sum to infinity will only exist if this condition here is met. So we are going to check R, we get the value of R, and then we are going to say since R meets the condition, then the sum to infinity exists. And then they say calculate the sum to infinity. At times they can ask you why it does not exist. Why does the sum to infinity not exist? Right. We move on here with the first solution set here. We calculate the common ratio as I indicated, and then from there we say that the common ratio is between what? Since R is trapped between -1 and 1, then S infinity exists. Then S to infinity exists. Then the second one says calculate the sum to infinity. Now we need A, we need R. We already have A is 16, we have R is a half. We've calculated it. So if we substitute there, we get that the sum to infinity is 32. So it converges to 2 like that. So the sequence or the series converges to 32. Right, we move on to example 4 quickly. Let's look at example 4. Let me first take you through it. We read together through the example and see. Example 4, consider the series 3x into x minus 2, 3x into x minus 2 squared, for which values of x will the series converge. Remember, the condition for convergence and existence of sum to infinity is that R should be trapped between -1 and 1. So we are going to work out R in terms of x, and then we are going to then subject it to that condition, and then we will know that the series will converge if the values of x are trapped within these parameters. Now, if the x value for the series, if x is the value for the series, if x is the value for which the series converges, sorry about that, if x is the value for which the series converges, calculate the sum to infinity of the series in terms of x. And then from there, hence calculate the actual sum to infinity if x is equals to 2.5. Right, let's go through the solutions together now. Now, let's check here. The first one, we are going to express R in terms of x so that we can check the values for which the series will converge, and which means that we divide T2 by T1, and then from there we get that this is 3 into x minus 2 divided by 3x. That gives us R is equals to x minus 2. Now, moving on with that, we know the condition for convergence is that R should be trapped between -1 and 1. And in this case, we have that R is expressed in terms of x. So where we see R, we will put x minus 2. So when we put x minus 2 like that, we get that x minus 2 is trapped between -1 and 1. And then if we apply our knowledge of the compound inequalities that we learned in grade 10, we see that we have -2. To get this to be x only, we are going to add 2 across. So when we add 2 across here, we get 1 and 3. So x is trapped between 1 and 3. If x is between 1 and 3, then the series will converge and the sum to infinity will exist. Right. For which values of x, or rather, if x is the value for which the series converges, calculate the sum to infinity in terms of x. So we are going to substitute the values in terms of x in the sum to infinity formula. There's the formula there. S sub infinity is equals to a over 1 minus r, we substitute a in terms of x, we substitute r in terms of x. So that substitution there is performed in step 2. You can see a is equals to 3x and r is x minus 2. So simplifying that further, we get that the sum to infinity would be 3x divided by 3 minus x. That would represent the sum to infinity in terms of x. Now, furthermore, they say that calculate the actual sum to infinity if x is 2, 5, which means that where we see x, we're going to substitute with what? 2, 5. So now, let's see here. We have s sub infinity, which is 3x minus 2, is the one that we've derived here. So now we are going to substitute 2, 5 wherever we see x. Let's see now. There we go. The substitution is made there. Where there was x, there is now 2, 5. So in order for us to then conclude, we can put this in our calculators. It gives us s sub infinity is equals to 15. Right, very nice problem. This very, very nice problem. These are types of problems that you should familiarize yourselves with. Right, the sigma notation. Now we want to talk to the sigma notation. Now let's look at the analogy behind the sigma notation. We are using the Greek symbol. That Greek symbol means sum. This Greek is the alphabet, is the letter S in the Greek alphabet. It means sum. It is used to symbolize the sum of any terms. That is why also in statistics, when you calculate the x bar, that would be the mean. You use this, you say the sum of all terms divided by the number of terms there. Now, this reads as follows. If you see here, you have that this is a sigma k equal 1 to n of tk. So now it reads as follows. The sum of all terms, tk, the general term, from k minus 1 to kn, where n is an element of all natural numbers. So n is an element of natural numbers. Very, very important. Now we read it as what? Sigma tk. So we say sigma, then the general term, then where it starts and where it ends. This is the lower index of summation. This is the upper index of summation. This is the nth term. So we will read it as follows. Sigma tk from k equals 1 to n. So that is how you read it. Sigma tk from n equals k equals 1 to n. So now calculating the values by using the sum formula. It is important to note that this thing here represents what? It represents the sum to n terms. Already we've worked out the sum to n terms. If it is arithmetic, we're going to use n over 2 into 2a plus n minus 1d. If it is geometric, we will be using Sn is a r to the n minus 1 over r minus 1, or the other way around if r is actually less than 1. So that tells us that whatever you sum up should be the same as when you sum it up using the formula. So that is key. Right, let's look at the application problems to sigma notation. Now, I need to show you how you can actually use the sigma notation to solve problems. Let's check the first one. The first thing that you're going to do is you expand. How do you expand the sigma? You are going to substitute the lower index of summation and go up and up, checking what the upper index would be. But remember, since the upper index is a very big value, we can just expand to get the first 3 terms, and those first 3 terms are going to tell us how the sequence will behave. So now if we expand this, where we see k, we put 1, 3 to the 1 plus 1, this is the first term, plus 3 to the 2, 3 times 2 plus 1, plus 3 times 3 plus 1. So this is how you are going to expand. K is equals to 1. Where there is K, I put 1. Then where there is K, I put 2 for the second term. Where there is K, I put 3 for the third term. And then from there, I will have my terms. So I will then be able to study those terms. There we go. 4, 7, K, 10 there. 4. So this is for sigma 3K plus 1 from K equal 1 to 50. So we generated the first 3 terms. We are going to use them to check whether it's arithmetic or geometric. If it's arithmetic, it means we'll use the formula for arithmetic terms. Now if you check this one, 7 minus 4 is 3, 10 minus 7 is 3, which means it's arithmetic. So we need to identify A and D, and then we use the formula to add arithmetic since these are arithmetic terms, right? So if we do that, we are going to substitute 50 over 2. Remember now, to get the number of terms would always be upper index, top minus lower index, bottom plus 1. So it's always with sigma notation, n will always be top n value minus low n value plus 1. So that is how you do it, top minus bottom plus 1. So now when we substitute there, we get that the sum to the first 50 terms is given by that expression. So now we get that the sum to the first 50 terms is 3,875. Hopefully that makes a lot of sense. Right, now I am going to move along with the activity. I'm giving you an activity on sigma notation. I'll request that you do this activity in 2 minutes. It's not a long activity. I think 2 minutes would be sufficient, and your 2 minutes time starts now. Right, hello and welcome back. Now let's do the same thing that we did in the previous problem. We should be expanding this. How do we go about that? 8 into 2, negative 2 into 1. We substitute 1 where we see m, plus 8 into 2, negative 2 into 2, plus 8 into 2, negative 2 into 3. You see, as n gets bigger, we put that on here. It's going to be used to expand. So when we've expanded that, it takes us to 2, a half, and 1/8, and then we study this series. When we study it, we can see that it contains a common ratio. So A is equals to 2, but R would be 1/4. R would be 1/4. That's how you actually work out R. We can divide T2 by T1 or T3 by T2. So A is 2 and R is 1/4, which means that we can still work out the number of terms. Remember, number of terms, top term, because we have infinite terms, it means that we are going to be adding sum to infinity. So we would use S infinity as A divided by 1 minus R. So in doing so, we substitute our values there. After substituting our values, we get that the sum to infinity is equals to 8/3. So we've summed up the terms using the sigma notation. Right, there is the next one. I want us to write the series in sigma notation. So I want to teach you how to write a series in sigma notation. Remember, we said this is the lower index of summation. This is where you start, this is where you end, and this is the nth term, or what is also referred to as the general term. What is also referred to as the general term. So now, if you want to write that in sigma notation, it means that we need to determine the nth term, and we will know we are starting from n is equals to 1 here, because this is T1. We don't know what n is here. That's where we're going to actually end. We know where we are starting, so we can actually work out the general term there. First, we determine the nth term. That would be the general term. By studying this, we can see it is arithmetic. A is 2 and D is 3. So because of that, Tn would be A plus n minus 1D. We substitute A and D onto that. We get that Tn is 2 plus 3n minus 3. Tn is equals to 3n minus 1. So that's what we have here. Tn is equals to 3n minus 1. Right, from there, we are going to then determine the number of terms in the series, because we have the term in the nth position. So we want to know what n is, so we can simply use the general term and substitute the value of the term in the nth position. So we work out that n 51 is equals to 3n and n is equals to 17. Now we have the general term, we have the nth term. We know we started at 1. We now know we are ending at 17. So we can take that and put it in the summation. Then we express in sigma notation like that. There we go. So we start at 1 to 17, and then the nth term is 3k minus 1. Remember, there is no issue with writing this in terms of n. N equals to 1 to 17 into 3n minus 1. You are still on the right path if you write it that way. Right, I think that this particular problem here, it made sense. The solution set to this problem made a lot of sense. Right, let's move on. Writing a series in sigma notation. Now this one is yours, a bit of a challenge problem. It's a challenge problem. We are indicating here that the following series is made up of numerators that form an arithmetic sequence and denominators that form a geometric sequence. Write down the series in sigma notation. So it's a bit of a challenge problem. I am giving you 5 minutes to work on that particular problem, and your 5 minutes time starts now. Right, hello and welcome back. Let us look at this one, the interesting one, um, where we have a combination of sequences, a quotient containing numerators that are arithmetic and denominators that are geometric. Now, in order to work with this one, what we're basically going to do is we will analyze the numerators on their own, analyze the denominators on their own. Remember, we want here where we start, and we know that this term here is n equals 1. However, we don't know where we end, and we don't know the nth term. So the nth term is quite tricky because we have numerators being geometric and denominators being what you call numerators being arithmetic and denominators being geometric. So it means we have to find or to determine the nth term for the numerators, the nth term for the denominators. That's how we should be thinking about it. And then as well, we need n. So if we want n, we can take either the denominators or the numerators and find the position of that term, because both of them are in the same position, both of them are in the last position. So it does not matter which one you use as long as you are going to use the correct formula there. Right, let us now consider the numerators. If we consider the numerators, we can work out the nth term of the numerator. So Tn is equals to 1 plus n minus 1d. We work out the nth term. So this would be the nth term for what? For the numerators. Nth term for the numerators. We can use this nth term to determine the position of the last term of the numerators. So we can use it. You see here we use 22, and then we determine that we are having 8 terms, which means that n is equals to 8. Remember, good people, even if you took it for denominators on the geometric, you are still going to find n is equals to 8. I'll show you this side. But first, let's work with the denominators. I want to determine the nth term. Denominators are geometric in nature. So a is 3, r is 3, and then from there we get that Tn is 3 times 3 to the n minus 1. Tn is 3 to the exponent of n. Now I just want to show you here. That alternatively, to work out n, we can still take Tn for the geometric and substitute 6, 5, 6, 1 is equals to 3 to the n, just to verify whether it will give us the same value as 8 there. So we can find the prime basis of 6,561. We get that this is 3 exponent 8 is equals to 3 to the n. Therefore, n is equals to 8. You see, it does not matter whether you use numerators or you use denominators, because both of them are in the same position. You are going to find that the value of n is the same. So we know where we started. We know that we started with n is equals to 1 and ended with n is equals to 8. We know that the general term contains what? Numerators and denominator terms. So in order to write the nth term like that, we are going to say, okay, we know we started at 1 and then we ended at 8, and then the numerators have the general term 3n minus 2. This is 3n minus 2, the general term for the numerators. The denominators have a general term 3 to the n, so this would be a Tn for the denominators, and that would complete what we actually wanted to work out. I hope that it makes sense. So such problems are problems you should be able to work with. You should be competent in solving such problems. Right, we move on. Given the sum formula. So if we are given the sum formula, we can then use this. If you are given Sn is equals to some expression in terms of n. If you are given Sn is some expression in terms of n, T1 would be S1, T2 would be S1 plus T1 plus T2, or S2 would be T1 plus T2, S3 would be T1 plus T2 plus T3. However, T1 plus T2 is S2, which means that S2 will then be, or rather, S3 would be S2 plus Tn, which means T3 is S3 minus S2, and hence Tn would be Sn minus Sn minus 1. So that is the formula we'll be using if we are given the sum to specific number of terms there. Now let us look at an example. A given sum formula can be used to determine the terms of a sequence, and in general we're going to be using that. So which means that sum to 10 terms. You see here they are asking us, they are giving us the sum formula, and they're asking us to calculate the sum to the first 10 terms. In doing that, we're just going to substitute. Where we see n, we put 10. So S sub 10 would be 2 into 10 squared plus 9 into 10. So S10 would be 290. That's simply how you work it out. Right, let's check the second one. The second one, they want the 11th term. So we will employ Tn is equals to Sn minus Sn minus 1. So T sub n, since they are looking at the, or they want us to determine the 11th term, so it would be T sub 11, it would be S sub 11 minus S sub 10 according to this formula over here. So we are then going to work out S sub 11 by substituting 11 on the original formula. We were supposed to work out S sub 10 by substituting 10, but we've already worked it out here, so we're going to just put the value there because we've worked it out. So we get that S sub 11 would be 51. So the 11th term is equals to 51. Wonderful. So that's how you work it out. That is the application of that particular formula. Now I have one last activity for you to do. This activity is very interesting. It will serve as the last activity for the day. It is activity 6. I want you to try and work out the solutions to activity 6. I am going to give you 5 minutes to try and work around that, and your 5 minutes time starts now. Right, hello and welcome back to the last problem of the day. Let's see whether you were able to work it out correctly. We are given that s sub n is n squared minus 2n, and we want to determine the 50th term of the series as well as the nth term of the series. So you see 50th term, not the sum to 50th term. There's a difference between s sub 50 and t sub 50. There's a difference between the two. If they say work out the 10th term of the series, they want this one. If they say work out the sum to the first 50 terms of the series, they want that. If they wanted this one, it was easier. We substitute n. When we see n, we put 50, but because they want this one, we should be using our formula Tn, which is s sub n minus 1 minus what? S sub n, like that. So see, that's what we use here. I wrote it the wrong way around, so it should be wrote it the other way around. S sub n minus s sub n minus 1. So that should be the formula there. So now in doing that, we just substitute. We need s sub 50 minus s sub 49, which will give us the 50th term. So how do we get that? S sub 50, we get it when we substitute 50 onto the original formula. S sub 49, we get it by substituting 49 into the original formula. Putting the result in the calculator gives us t sub 50, which is the 50th term, is equals to 97. Now, very interesting, this one, a high order question, very nice. They say determine the nth term of the sequence here. Determine the nth term of this. Obviously, you can take it with t sub n, which is sn minus 1. So we are going to substitute that of sn, which is n squared minus 2n, and then n minus 1 as n minus 1 squared minus 2 to the n minus 1. Remember, there's an alternative approach here that you can take by just working out. You can work out t1, t2, and t3 by using this formula. After working it out, then you can determine the nth term. However, the formula itself also allows you to go directly. Now, obviously, when we have that, we can simplify on this particular bracket. By applying the distributive property, we get that this is n squared minus 2n here. When we apply distributive property there, we get n squared minus 2n plus 1. If we distribute here, we get that this is 2n plus 2 when we apply distributive law there. So now we get that we can simplify. So we get that Tn, if we simplify this, we see 2n and 2n gives us 4n, 1 and 2 gives us 3. So we can then open the bracket, the second bracket, by using the distributive law here. We see that this would be negative n squared plus 4n minus 3, like that. So when we simplify, the n squared and the n squared will become 0. They add to 0. Negative 2n and 4n, they add to 2n, and then you're left with 3. So you have that the nth term is 2n minus 3. So that is the way in which you were supposed to attempt that. I think that some of you might have gotten it correct. Those that did not, you now know how to work around it. Good people, I think we've done justice to the work that we were supposed to do today on geometric series. So we go through the summary now. We are saying when working with patterns or series, one must know the type of a series they are working with. The constant difference or constant ratio must be determined, and the correct formula to be used must be identified. That's very, very important. In an arithmetic series, finite terms are added. Sum to infinity is only applicable in geometric series that are convergent, and the condition for convergence is R should be greater than -1 and less than 1. And if r meets that condition, then we say the sum to infinity exists. Right, good people, thank you very much. We will see you next week when we start our work on functions. Please take care of yourselves and take care of each other and practice mathematics. Goodbye.